It's Aleksi Kurkela from Stavanger and CERN, I guess. And he is going to talk about quark matter in neutron stars. And yeah, I see the slides. Aleksi, are you around?
Yes, can you hear me?
Yes, perfect. Ah, there you are. Okay, so I guess you're a bit early, but I think you can start with your talk.
Okay, thank you. So first of all, thank you for the kind invitation to give this talk here. So as Richard mentioned, this is going to be a little bit of a different topic from the very quantitative and detailed talks that we've had so far about specifics of hot quark matter. And here I just want to pose the qualitative question: how and if it is possible to tell that there would be quark matter inside the cores of neutron stars as well. And this is some work that I've been doing with my collaborators over the last decade, actually. And here I have just on the first slide some references here, mainly to point out my collaborators there. This picture that you see here, there's somebody has a microphone on that there. A little bit makes noise. But anyways, this picture here is a illustration picture of this recent paper with these gentlemen, where we make the case that it is plausible that there would be large cores of quark matter inside the cores of the most massive neutron stars in that can exist stably. So of course we've heard already many talks in detailed way describing how in extreme conditions hadronic matter reveals its partonic constituents. When we heat up or compress hadronic matter due to extreme enough conditions, the nuclear matter gives way to elementary particle matter that we call quark matter, or if it's hot, we call it the quark plasma. In addition to this studying quark matter theoretically, of course, we can study it empirically. And actually, we are right now in a very privileged time in history to study quark matter. There's the precision frontier in the accelerators, such as the LHC coming runs 3-4, and the high Lumi LHC that will describe the properties in unprecedented detail and accuracy of hot quark matter. And of course, we have these extremely interesting dedicated experiments like the FAIR and NICA coming up that study quark matter at slightly lower temperatures but higher densities. But at the same time, we have a completely new window to extreme hadronic matter, which comes from the discovery frontier of ultra compressed hadronic matter in the cores of neutron stars. This new window of multi-messenger astronomy, now we have gravitational waves originating from mergers of neutron stars, and at the same time there has been a gradual progress in X-ray astronomy that gives us better and better measurements of properties of neutron stars in the X-rays. Now, if I had to summarize the conclusions from collider experiments, 3 decades of experimentation with nuclear beams, I would say that the main message that we've learned is that around the energy density of 500 MeV over Fermi cubed, there's a transition from hadronic matter to quark matter. There's not a strong first order phase transition, there's a smooth transition, but we see that the characteristics of the equation of state change when you cross this smooth crossover temperature. Now in neutron stars, these energy densities are quite easily reached. We don't know what the energy densities in the neutron stars are, but they can be easily at this level. And so that, of course, makes me ask the natural question, could there also be deconfined cold quark matter inside the cores of neutron stars? Now, if I take a step back and I ask, how do we actually, why do we believe that we have quark matter in hadronic collisions? There is no true phase transition going from hadronic matter to quark matter. So there is no smoking gun evidence of formation of quark-gluon plasma. There's no bubble wall explosion or something like that that could be accompanied with the first order transition. And we don't have a smoking gun evidence of where the quark-gluon plasma is generated. And the reason why we believe that there is quark matter in heavy ion collisions, the argument heavily relies on results coming from lattice field theory. Here is, of course, the famous plot of pressure as a function of temperature. This one is from the Wuppertal group, which shows that even though there is no first order phase transition between the two phases, still these two limits, the low density, or I should say low temperature limit, low energy density limit, is described by models based on hadronic degrees of freedom. So here is the hadronic resonance gas model showing beautifully how it follows the lattice results. And at the same time, at the very high densities, the characteristic features of the equation of state resemble of those that come from calculations with partonic degrees of freedom. So of course this plot has been normalized by T to the fourth, such that if we would have free quark-gluon plasma, this would be a constant. And as you can see, the equation of state is becoming roughly a constant, showing that the equation of state is approximately approaching a conformal matter. There's a small discrepancy between the normalization, but the ballpark is there. So all in all, as you go to high temperatures, what you see is that the matter resembles nearly conformal quark matter. And there's different kinds of ways how you can quantify that. You can characterize the equation of state. For example, looking at the polytropic index, which is the logarithmic derivative of pressure with respect to the logarithm of energy density, which just means that this goes to a constant, and it certainly does go to a constant. And the number of active degrees of freedom, so the normalization here, is roughly what you would expect from matter made out of gluons and quarks. And the speed of sound also approaches the conformal limit from below. Here in this plot, you also can see calculations which are not just free quark matter calculations, but have interactions. This is a recent hard thermal loop calculation. And where you see that it may be that there are large uncertainties in the perturbative calculation here. However, the overall trend, the shape, for example, that gamma is 1, meaning that these lines are more or less constant. These are characteristics that are particular to quark matter. And the normalization is roughly there. So you can see that there's two regions, a region where the equation of state is roughly described by hadronic matter, and then there's a region which might not be in the convergence region of the perturbation theory, but still is described roughly by the characteristics of partonic matter. And then, so how do we know that we have quark matter in hadronic collisions? Well, in hadronic collisions, what we can do is we can measure the energy density of the system, or we can at least estimate it. We can compute how much particles fly away and how much energy they carry from the interaction zone. And because we know roughly what the volume of a nucleus is, we have a pretty good understanding of what the size of the fireball is, and that gives us a estimate of the energy density of the system. And these energy densities are well above this region where your equation of state turns into a quark matter-like region, and hence we conclude that the matter that we create is quark-gluon plasma. Now, here, of course, as a side remark, there's a strong burden of proof in theory, because we have to discuss if this matter created just flies away from the collision zone, or if it actually has time to make a proper thermalized system. And that's where most of the theoretical work in heavy ion community goes, and also experimentally. That's why we need sophisticated modeling in hydrodynamics. We need understanding of electromagnetic radiation. We have to connect this hydrodynamics to jet quenching and so on. That's where the questions go, whether or not you have a thermalized medium. But assuming that that is the case, then we are well in the high energy density phase, and that's why we believe that we have quark-gluon plasma. Now, what I would like to do is I would like to take this same logic here, and I would like to apply it to neutron stars. Of course, there the challenge is twofold. So there were two inputs that this logic needed. One was that we have the equation of state from the lattice, and the other one was that we can have a measurement of the energy density. Now, when we go to neutron stars, we don't have the lattice simulations because we have the sign problem, which prevents us from doing lattice simulations. And we can have reliable first principles calculations only at low densities and at very high densities. Of course, we can do models in between, but if we want to restrict ourselves into ab initio calculations, these are the limits that we have at our disposal. And the second problem is that we don't have access to measure directly the energy density at the center of the neutron star. So we can only, we cannot measure dE perp over d eta, but we have only access to global properties such as the masses and radii and so on. However, here we what comes into our aid is that the structure of the neutron stars is given by this competition between the pull of gravity and the pressure of strong interactions, and because of this interaction or this competition, the macroscopic properties of the stars are dictated by the equation of state, by the material properties of the strongly interacting matter. And because of this competition, these neutron stars act as nature's own femtoscopes that magnify the physics coming from the nuclear scale into the 10-kilometer radius scale of the neutron stars. And because of this competition, what we can do is we can at the same time try to address both of the problems that I had in the previous slide, which is that we can try to use the properties of these neutron stars to constrain the equation of state where we cannot calculate it from first principles, by looking at the macroscopic properties of these stars. And at the same time, when once we have an idea of what the equation of state can be, we can then reverse engineer what the density profiles of the neutron stars, for example, should be. So we don't have this nice separation of doing a theory calculation and a measurement, but because we don't have lattice simulations, they have to somehow come at the same process when we try to apply the same logic to neutron stars. So what I'm going to now talk in the rest of this talk is I'll tell you what we know from the equation of state from first principles of initial calculations, and then I will try to discuss what does that what can we say, what does that imply about the energy densities inside the neutron stars, and how we can use that information to address the phase of the matter in the core. So if you start digging yourself inside the neutron star, you first start from the outer crust where this is not really QCD physics. What you have is a degenerate electron gas, very much like in a white dwarf, and then you have a lattice of nuclei with increasing number of neutrons as you go inside the deeper and deeper to the neutron star until you reach the neutron drip line and you start having free neutrons in your system. You can go deeper or denser in the neutron star until you reach roughly the nuclear saturation density, the density that is inside the largest atomic nuclei, and at that point the interactions among the neutrons become extremely important. Up to this point, we somehow understand the equation of state extremely well, and if you want to go further, you can use the state-of-the-art nuclear theory machinery. You can use chiral effective theories based on power counting methods that translate the terrestrial nuclear experiments into predictions of equation of state. But these methods run out of steam at rather low densities, roughly. This particular calculation here runs out of steam around 1.1 nuclear saturation density, mainly because of lack of knowledge of more low energy constants that would come into the chiral effective theory. At the same time, we know that at very high densities, QCD, coupling constant runs, we have a hard scale being the quark number chemical potential. And eventually we know it's a non-negotiable fact that at very high densities we will reach the pressure of free quarks, similarly to the free quark gluon plasma in the finite temperature case. And so this is non-negotiable fact. So we know that this low energy limit here has to at some point asymptote to this free quarks here. However, it's not a very useful constraint if we don't know how and when do we reach this asymptotic limit. And if we want to understand better, to turn this into an actually quantitative question, we need to understand how and when is this limit reached. And for that, one needs to do high order derivative calculations. The parametric form of higher order corrections is the following. So this is when you compute the pressure to leading order, you're just integrating over the Fermi sphere, over the dispersion relation of your particles, if you wish. When you go to next to leading order, all the expressions in this leading order expression get a correction that comes with g squared. In particular, the square of the dispersion relation gets a g squared correction, and that translates eventually into a g squared correction to your pressure. Now, if you go to higher order corrections, you have also higher order corrections to these terms, and you get a series expansion in g squared, and you get higher order corrections that can be computed in loop expansion. But in addition, you get an additional component, which is that if you have a momentum which is roughly of order g mu, then these corrections become order 1, so they become non-perturbatively large, and there is a contribution of wavelengths of order 1 over g mu, where you have to supplement your perturbative calculation with a non-perturbative calculation, and because you have these two scales appearing in your calculation, you will also get logarithmically enhanced parts of the calculation which are sensitive to these long wavelengths modes, and the short wavelength modes at the wavelength of order inverse mu. So that's somehow the parametric form. In practice, what you do is you need to compute high order Feynman diagrams. The normal perturbative calculations come with these fixed order loop expressions, and the non-perturbative parts come from resummations of diagrams with infinite number of loops. And where we are at now is that the next to leading order comes from one diagram. It's known any way you want. At the next to leading order, we know the full temperature dependence and full mass dependence, and we can go smoothly between the high temperature regime and the high chemical potential regime in same calculation. And right now, what we are working hard on is trying to compute the next to leading order, where we have computed so far we've computed the leading logarithmic part of the next to leading order calculation, and we are working hard to finish the calculation for the next to leading order logarithm, next to leading logarithm. Okay. I will skip that. So at the end of the day, this is what the result looks like. Here is what I show. Here is the pressure divided by the free quark matter pressure. So it's the analog of P over T to the fourth. This is now P over mu to the fourth with some coefficient there, such that free quark matter is this red line here. This blue dashed line here is a particular bag model that has sometimes been used in phenomenology. And this red band here is our result, up to and including the next to leading the leading logarithm of the next to leading order, next to leading order. And the first thing what you see is that the interactions matter. You can go to very high chemical potentials, and still you are far away from the free quark limit. And the other thing what you see, of course, is that there's an error bar, and the error bar comes by using the standard technique used in high energy physics calculation, which is the varying of the renormalization scale. You pick a fiducial renormalization scale, which is the typical energy scale in the system given by the chemical potential. The green line here, that is one calculation, and then you vary the renormalization scale by a factor 2 up and down, and you get your error bar here. And you see that the error bars are small if you're at high densities, and when you reach basically the nuclear chemical potentials at this point, the perturbative calculation kind of knows where that happens, and that's the point where roughly where the error bars blow up, and the calculation, of course, goes wrong. Now, because we can connect these calculations at 0 temperature to finite temperature, we can smoothly go to the finite temperatures, and we can estimate the reliability of our error bars by comparing them to the lattice simulations where they are available. And here you can see that this is a calculation at high temperatures. This is at high densities, and at high temperatures you can see that the perturbative error bars roughly give you the idea of how far you are from the lattice state. Okay. So that's what the equation of state eventually looks like. Here is the low density side, here is the perturbative result, and the errors here are measured to the low energy calculations, roughly around 40 nuclear saturation densities. The densities that are reached in the course of neutron star are somewhere here, so it's clearly far away from these calculations, which get you into maybe half a kilometer into the neutron star. But you are still quite far away from the perturbative limit as well. So the course lives somewhere here in the truly interesting region. And by the way, just as a side remark, these are the densities where you reach the same energy density where quark gluon plasma is reached in heavy ion collisions. So you might very well be on the right side here. Okay, so what you can do in this no man's land is you can indeed use the fact that we have astronomical observations of the stars, and the strategy that we followed, and Aleksi Kurkela will talk about in detail that strategy tomorrow, I think, is to take these two limits. This is a different way of plotting the same equation of state. Take these two limits and then draw lines between them in all possible ways which don't violate any fundamental physics reasoning, like speed of sound being less than speed of light, or thermodynamic consistency, and so on. And Aleksi will talk about this process much more. I'll just show what the results are, because now once we have this set, this is by the way a set of 200,000 different equations of states, combining these two limits here, we can build stars out of them, and we can rule out any stars, any equations of states that are not compatible with the neutron star measurements, such as these. All these equations of states which are not green do not support a 2 solar mass neutron star, and we know that there exists a 2 solar mass neutron star in the sky, so we can rule this out. And for example, the gravitational wave observations rule out another set of equations of states, and I'm sure Alex will talk in detail how that happens. And at the end of the day, that's the set of equations of states that we are left with, and that somehow is what our version of lattice determination of equation of state is. This is the set of equations of states which are consistent with our understanding of theory and our understanding of astrophysics or astrophysics observations. And so you can think as this set of model equations of states between these two limits as somehow a empirical determination of the equation of state. Now let me go to my final topic, which is to ask, do we have quark matter? So first of all, we have to ask, how do we see quark matter in this equation of state? And if I look at this equation, or do we see quark matter in this equation of state? If I look at this plot here, what I see is that there's very strongly the astrophysical observations make this happen, by the way. I see a two-phase structure appearing. There's a low density phase here, which seems like an extrapolation of the low energy density limit. And we have a high density phase here, which seems like a extrapolation of the high density limit. Here we don't have a controlled perturbative calculation, but what it seems like is that the equation of state works like we would expect a matter made out of partonic degrees of freedom coming. So here we see that in this region, the matter roughly looks like conformal matter with the right number of degrees of freedom, and so on. We see that and here in the low density phase, we see that the behavior is very much following the trend set by nuclear theory models. And this bend between the two phases happens roughly at the same energy density, a little bit higher than in hot quark matter. And so these all are somehow hints that this kink, the physical meaning of this kink probably is that the active degrees of freedom in the matter are changing from nuclear degrees of freedom to partonic degrees of freedom. And that's probably the point where the quark matter sets in. Now, we have so this is just one observable, and we could look at many other observables, but I will leave that to my collaborator to talk about tomorrow and go through the more detailed argument why we believe that this change of the slope is a reasonable proxy for where the transition from hadronic looking matter goes into a partonic looking matter, And I will just make the point that if you take this kink as a sign of partonic matter being formed in the core of a neutron star, you can then ask for a given neutron star, how much is there matter that sits on the right hand side here, and that's given here. This shows that it is possible that we have very little amounts of quark matter in the stars, but in many models that we can have, it seems that in particular the most massive neutron stars that are stable can harbor cores that contain a significant fraction of the volume of the neutron star and the mass of the neutron stars. And actually, we, in particular, in this particular study published here in Nature Physics, we found that if the speed of sound in the neutron star never exceeds 1/4 square root of 0.4 of the speed of light, then there is always a good amount of quark matter. And even if we don't have quark matter, it seems that the collapse of the neutron stars is triggered by the onset of a phase transition, first order phase transition, where this quark matter appears. Of course, we cannot at this point make very strong claims that there's a particular neutron star in the sky where there would be quark matter. We are not there yet. We are talking about the most massive neutron stars. However, in the future, this picture will certainly get more tight. There are active calculations in nuclear theory trying to push these densities to higher, where you can trust your calculations. We are certainly working hard to bring down the perturbative calculations, and we have a wealth of data coming from astronomical observations that will make this equation of state much more constrained in this intermediate density region. And so in the future, I hope that we can make, and I believe that we can make significantly stronger statements about existence or non-existence of quark matter in specific neutron stars. So let me finish by going through my key statements as we were asked. So I think the existence of quark matter in heavy ion collisions is established not by a particular smoking gun signal, but by establishing that energy densities are reached where matter is better described by nearly conformal partonic matter, better than hadronic matter. It may be that in case of neutron stars, there may be a smoking gun evidence because there may be a strong enough first order transition so that would lead into something that we can without theory, without fundamental QCD theory, associate with a phase transition from nuclear matter to quark matter. That is a possibility. But it's also possible that the first order transition is smooth enough, or you don't even have a first order transition. And if that is the case, then we won't have a smoking gun, and then the existence or the non-existence of quark matter will be established based on precise information about the material properties in the core. And if that is the case, then calculations like I described, based on fundamental QCD theory, will play a key role. And I mentioned our results, which pointed out that we have hints pointing that quark matter exists in maximally massive neutron stars. We don't have definite answers yet, but it should be treated as a standard scenario because all the alternatives from the QCD point of view are more exotic, if you wish. Thank you.
Yeah, thank you, Aleksi, also for staying in time. We are just on time for a short break, but maybe somebody has a short question for Aleksi.
Yes, I would like to ask.
Yeah, David.
You showed this one graph where you indicated the region of energy densities for the hadron to quark matter transition in hot QCD, so in the lattice. And you made a point that probably in cold matter, this transition region should be located, as you indicate, maybe at a bit densities. Is there some reasonable heuristic argument for this? Or I ask because there are claims like from Rafelsky and Petran that in heavy ion collisions, when you look at the border between quark-gluon plasma and hadronic matter and chemical freeze-out, that there is some indication that there might be a universal transition energy density and universal pressure.
So I think the way to think about it is that if you come from the quark-gluon plasma side, there you are in that side of the phase diagram, you are conformal. So then energy densities and pressures are proportional to each other, and then that is the natural place where, I mean, it doesn't make such a big difference if you're at finite temperatures or densities where you would expect something to happen. Of course, coming from the nuclear physics side, the matter is very different. But I'm not claiming that somehow I'm not claiming that it has to be there. I'm just pointing out that the energy density seems to be there, and to me at least it seems natural that if I come from the conformal side, the energy density should be roughly the same.
Because I said you know that since many years now we experiment with twin stars with very strong transitions, which are fulfilling then the compact star constraints. And what we find is that the transition pressure in such situations is of the order of so between 10 and 100 MeV per Fermi cube, and the corresponding energy densities coincide with the region which we find in lattice QCD transition. Only that the transition is more pronounced at low temperatures. It is at high temperatures, it is then smoothed out. Yeah, that's
right. So I don't have a strong argument why this would have to be so, unfortunately.
Thank you.
Maybe we can also come back to this in a few minutes and have a short technical break now. I think the idea is we now have a 10-minute break and then start our discussion session.
Yeah,
So
yeah.
we come back. We all come back in 10 minutes from now. Okay, thanks everybody, all the speakers, and I'm looking forward for an active discussion.